Yeah, so I'm going to talk about a thread of work that's been going on in my research group for 10, 12, 15 years, maybe even, on domain-specific compilers, domain-specific languages, program generation. And I'll show you what I mean by that. And I'm really talking about the DSLs, not the ones that help you program for a specific target hardware, but the ones where you type in the equations you want to solve at the beginning. And we have tools that really benefit from the tool chain knowing what the problem you're solving really is. So I'll say a lot more about what I mean by that. This is joint work with a great number of people, and the list on the slide is incomplete, but I'll show some citations as we go along to some of the papers that I'm going to be referring to. So who am I? What do I do? Well, I've worked on lots of things, as Gil kindly introduced, and including compilers for general purpose programming languages. For example, I'm particularly proud of one of my PhD graduates, David Pierce, who built a pointer analysis which got adopted into GCC and is cited from people from the LLVM and the Golang compiler and so on. And that's fantastic, but in fact, the benefits were pretty incremental. Compilers are not very good at understanding what pointers are doing in programs, and this is one of the fundamental barriers that limits what optimizations are possible. And sometimes it's because the analysis is dumb, and we've pushed on that a bit. The truth is that even heroic interprocedural analyses don't get you very far, partly because the pointer sharing and so on is data dependent. And it truly is possible that there might be data that messes with the parallelization strategy, and sometimes it's even normal. And yet there remains parallels, for example. So, meanwhile, I met people doing exciting applications, and they really, really know. I mean, one of the things you learn from talking to computational scientists is that very often they know a lot about how to optimize what they're doing, but it's a huge amount of work. So I got interested in talking to them about what they were doing and automating what they told me about how we should solve their problems. That led to Firedrake, which Georg mentioned, and DeVito, and I'll tell you about both of those later in today's presentation, and also peripherally in another tool called PyFR, which is kind of similar. These are all tools where you type in the partial differential equations you want to solve. You specify discretization, and the tool automates the textbook numerical methods and generates high-performance code. So we're simultaneously trying to get the benefits of really a very high-level abstract programming model and the performance you get when the tool chain really knows what you're doing. So hopefully it's a win and a win. And so another thing we tried to do is to pull off the same trick in robot vision. We did lots of fun things with robot vision people. None of them is a DSL. We're working on it. There's a kind of big picture of what we do in my software performance optimization research group. On the left, we see a bunch of compiler technologies, code synthesis technologies. In the green, we have application context. So often they're characterized by a numerical method. So we see here finite element, finite volume, finite difference, and things like density functional theory, ab initio computational chemistry, and a bunch of other things. And what we try to do in orange is build mostly open source software tools that apply red stuff to the green stuff to solve problems in blue on the right. So the orange part is the bit we actually do. The blue part is really not what we do, but it's what people have been doing with the tools that we've been building. And this is really fun as a compiler person, right? You go to parties, and there are certain kinds of parties where you can talk about compiler technology and everybody thinks it's wonderful. Very often you find that the things that really make a difference to what people are interested in are much more application focused. So I have friends who think I do fluid dynamics. I truly don't do fluid dynamics, but you get sucked into talking about these applications. We do a bunch of other things, and I won't spend too long talking about that, other than to acknowledge that I have a career problem with getting involved in too many different kinds of things. And as a junior academic, this was actually a problem. I got told at review meetings that I should focus. As a full professor, it's a privilege of being an academic, and I've decided to just run with it. So this talk is, I'm trying to focus on compiler architecture, and I'm not really going to talk much about compiler architecture, other than to kind of highlight its potential and its power and its importance. through some examples and a little bit on some of the technology that might support you in compiler architecture. And I'm picking the title because it's slightly underappreciated. If you read a classical compiler textbook, the design of the intermediate representation in the compiler is important and is discussed. When you're looking at domain-specific compiler architecture, it becomes the most important thing. The importance of capturing application code at the highest possible level of representation so that things that might have been really hard get much easier. That's what it looks like to win, and I hope I can show you some examples of that. So we're trying to capture what the code is trying to do, capture what we need to do to optimize for different kinds of hardware, and consequently build backends that target all sorts of exotic kinds of hardware. All right. Before we do that, I thought I'd just tell you a couple of things that I've been enjoying thinking about recently. One of them is this, the Turing tax. Now, I didn't invent this idea. I heard about it from a friend who denies telling me about it. But anyway, the Turing tax, you might call it Turing tariffs. This is, imagine that you've got a problem that you need to do and need to solve, and you have a general purpose computer that you can program to solve it. You might ask, well, how much better could I do in performance, in energy, for example, if I were to build a fully specialized application-specific integrated circuit for this problem? Now, this is not because that's a sensible thing to do. It's a thought experiment to ask yourself, where's the price being paid? Now, a general purpose computer is fundamentally a fetch-execute machine, and that fetching and executing is actually part of, you might hope to specialize that away in a fully specialized ASIC. There are many other things, indeed, many of the things you find in a compiler textbook, in a computer architecture textbook, are either gratuitously increasing the Turing tax in order to go faster, or, for example, with vectorization, we're trying to amortize some of the Turing tax. So there's lots to think about there. And when I teach computer architecture, I kind of think of it that way. One of the reasons I'm telling you about this presentation is to ask whether it applies in compilers as well. So this is another diagram that comes from teaching compilers. Roughly, you tell students there's a front end of a compiler that analyzes stuff, and there's a back end that generates code. And we don't teach all of this stuff, but all this complicated analysis, pointer analysis, data flow analysis, polyhedral analysis, data structure shape analysis, all kinds of stuff like this. What we're trying to do is to build a representation in the middle, capturing everything we can know from compile time analysis of our program, so that we can go downhill and generate the best possible code. And the analogy with skiing, compiling is like skiing, is this is an uphill trudge. And sometimes we have automation, we have tools, we have ski lifts or something that can take us some of the way up. And the higher we can get, the better the paths down the mountain are, the better the code we can synthesize will be. So the higher we get, with a DSL, we might hope to take a helicopter ride to the top of the mountain. We should not have to do any of this climbing up the mountain with static analysis. Instead, we should know, because of where the code came from, all the things that we need in order to be able to really capture everything we need to exploit or to implement, to automate, all those things that those domain specialists knew about and more. So carrying your skis up the hill is not the best bit of a skiing holiday. I would argue it's kind of Turing tax or Turing tariff or whatever. It's the price you pay for coding in a general purpose programming language, instead of using a DSL that gives you the helicopter ride. And I'm being provocative here because we usually think that coding in a low-level language is the way to performance. And, it kind of is, if you're prepared to put the work in. We can automate this stuff for a family of applications. That's the point. All right, so compiling is like skiing. Let me show you, this is the first of two main examples of DSLs I've been working on that I think make this stuff come true. So Firedrake is a tool which automates the finite element method for solving partial differential equations. It implements a DSL called the Unified Form Language. And actually, we didn't invent this. This came from the Phoenix project, with which we share much of this conceptually, and to some extent code as well. We re-architected quite a lot of the compiler architecture and get better performance most of the time as a result. They've been catching up. So this is the work of a substantial team of people, many of whom are shown here on the right. And I would highlight David Ham is the professor in maths at Imperial, who really these days leads this project. I got involved as the compiler specialist. I learned a lot about their problem, but these days, this project is kind of driven from the applied maths side. And I kind of think of that as a success. They still have problems that look like compilation problems. Some very interesting and tricky things, for example, in generating really good code for GPUs for this kind of problem. And I'm talking to them about it. Let me tell you a bit about, so Firedrake is not just a tool as I've described it. It's also a kind of center of an ecosystem of different things. In fact, on the right here, these three tools are examples of tools which are built on top of Firedrake for particular application domains. So Thetis, I'll show you some examples of the work there in a second, is primarily an ocean model for modeling the way the ocean flows around coastlines, and it's been particularly used for energy applications. I'll show you that in a second. IcePack, basically somebody at a polar research center found Firedrake and started playing with it to model the way glaciers flow. And he got sucked into our developer community, which was fantastic. Gusto has been used to prototype the numerical methods for the next generation of the UK weather model, the UK Met Office weather model. Those are application-focused extensions or part of the ecosystem. And then we have a bunch on the left of other examples of people doing very interesting things. So parallel in time, for example, is where you want to run something for many, many, many time steps, but it's not a very big problem. So what you'd like to do is to accelerate this by domain decomposition in time in order to parallelize this problem. And they have algorithms that actually work on that. Another really big and important one is Firedrake Adjoint, which builds on work from Phoenix people, actually. And this essentially is where, because we're capturing a mathematical model of what's going on, we get automatic differentiation for free. Or rather, in the PDE world, the derivation of adjoint PDE solvers. And this opens up a world of inverse problems, of solving for the optimum shape of a blood vessel, that kind of thing. Or the optimal, solving for the initial conditions, for example, for a flow behavior that you've observed, this kind of thing. And indeed, we have further work that plugs this into PyTorch and JAX, exploiting this capability to do automated, integrated learning of material properties, for example, where we have a neural network that characterizes the way steel bends or something like this. So as an ecosystem, let me show you what this thing actually does. So on the top here, so this is a test problem of the Burger's equation, test fluid dynamics problem. And this is a step in the mathematical derivation. What we have here is the equation that needs to be solved to discover the next time step, un+1, from the current time step. And what we're going to do is we're going to assemble a linear system and then use a linear solver to solve it. And what Firedrake really does, most of the work in Firedrake, is on assembling the linear system efficiently from the mesh. So what you do is you take this and you transcribe it into Python, as shown here. And if you look carefully, you'll see this is actually essentially the same expression as the left-hand side of this equation. Having constructed this, forgive me, this happened again, you might then simply solve for whatever makes this left-hand side 0, solve for the u that makes this, the un+1 that makes this thing 0. So here's the code, right? On the left is the complete code to solve that Burger's equation on a mesh that we specified up here. I'll show you. And down here is the line of code that I just showed you. Let me just show you that a bit bigger. So down here is the line of code that I just showed you. In here, over here, is the solve f equals 0. This is in a time-stepping loop, right? We're going to iterate multiple time steps. We're then going to project the quadratic mesh, finite element mesh, into a linear interpolation so that we can visualize it in VGK. Up at the top, we're specifying the mesh on which this finite element solution is to be calculated. So this is a conjugate gradient mesh. It's the mesh on which we're doing the solution is order 2, it's quadratic. The mesh on which we're going to output is order 1 linear. Sorry, again. And what the compiler is really doing is weaving together the mesh or the finite element model with the finite element discretization with the PDE to generate the code that assembles the linear system. And then down here, what we're going to do is call out into PETSI, call out into a standard solver library. And for more serious applications, you may add some parameters here that essentially get passed straight into PETSI to configure how the linear solver should work. So you have full access to the full richness of the PETSI solver. All right, what's the compiler do? Well, it generates C code, or perhaps CUDA code. This is a simple example, and I'm not expecting you to answer questions on the detail of the code I'm showing you here. Of course, in complicated examples, this gets much, much more complicated. I mean, many, many pages of code. What's going on is, firstly, at the beginning and at the very end, actually, what we're doing is we're capturing the data that the kernel depends on from the mesh. So we have an abstraction in the compiler toolchain for a declarative specification of how a kernel should be fed from the mesh, and that yields this code here. Down here, we're going to compute the integrals. Essentially, we're going to compute the elements that go into the global system matrix, and then down here, we actually pass those into we do the global system matrix assembly. Here is a section where we are evaluating redundantly or evaluating common subterms that appear in those integrals. And this is a crucial thing for the performance of tools like this. So you might ask, I mean, this API is 100% Python. It's very high level. Is this just a prototyping tool and you have to go and implement this in some low-level language? I would argue not. So this slide, for more details, you might go look at our paper. It's about the performance of vectorization. So this is all on an AVX 512 machine. And what we have here are 5 different, essentially, PDEs of increasing complexity. So hyperelasticity is really complicated. And these are on different kinds of mesh. So we have triangular mesh, quad meshes. These are unstructured, but quad, tetrahedral in 3D and hex in 3D. And for each of those points, we have 6 versions of them for polynomial order, ranging from linear all the way up to a polynomial order of 6. So, for example, we could pick these nablas here. Oh, sorry, these orange ones. So, for example, these up here are different polynomial order implementations of hyperelasticity on TETs. And in fact, the flop performance that's being achieved here is pretty spectacular. So this roofline diagram shows that this is totally flop limited. And indeed, you can get a flop rate faster even than Intel's LinPack implementation. And you might think that's fantastic. Actually, it's really not fantastic because there are much, much better ways to solve a PDE than that. And if we look at solving the same equation using hexes, we can live in this green world where things look much, much better, and you can't quite see what's going on here. But some of these are even borderline memory bandwidth limited. Why? Because when we go back to this here, for those tensor product elements like quads and hexes, we're able to do massive common sub-expression elimination. And that leads to loops that compute vectors of terms which are then going to be reused in the assembly process. And that leads to a thing called sum factorization, which works for those tensor product elements, meaning that you should live in the green world, not the brown one. So some applications were totally memory bandwidth limited, and you might wonder what to do about that. We've explored various tiling optimizations, for example. But you might also talk to users about how they might climb this and modify the numerical methods to exploit the hardware more efficiently. Good. So I promised some compiler architecture. Here's a rendering of the architecture of the Firedrake compiler. So at the beginning, you type in this unified form language, the one that we adopted from the Phoenix project. You can actually input code from other, you can also code more directly. And we've had users who've done things that couldn't be done in UFL, prototyped them, shown how they're useful, and then we've automated them and adopted them into UFL. The first step of this compilation process is to produce this intermediate representation. It's a tensor contraction. It's an Einstein notation representation for what happens when we visit an element of the mesh. So from there, we get a representation called loopy, which is essentially a loop tree representation. And that forms the body of the kernels that I mentioned earlier on, where the kernels have a kernel that operates only on local data, local to a mesh element, and then a declarative specification of how that kernel is to be fed from the mesh. That's what the PyOP2 layer is. And in fact, we have a new version of this called PyOP3, which does it better because it understands meshes better. Then we have more optimizations. For example, that's where vectorization happens and CUDA code generation. And we have backends for multi-core and clusters and GPUs. We've done GPUs before. We've been chasing GPUs for a long time. What actually happened was that one of the first things we did was we built a GPU backend. And then we built a vector backend, and we realized that we could make it much faster by doing some of those redundancy optimizations. And now we have to go back and deliver that into the GPU backend. And then questions of how you generate code. It got complicated. We're working on it. If bits of stuff work in GPUs, we'll land it soon. But, I should say that common sub-expression optimization that I mentioned, we first implemented that over here in the loop transformations here. So we implemented it as a loop optimization, essentially the way a classical compiler would do it. It's a generalization of loop invariant code motion to loops that are deeply nested. And that was great. We wrote a paper about how for certain classes of applications, we can get, in some sense, literally optimal code. But it was a mess. Then one of our PhD students created this layer of the compiler, the tensor contraction layer. And then another PhD student realized that he could implement all of that complicated stuff as tensor factorization in that algebraic tensor contraction representation. And we got to delete thousands of lines of code over here, which is one of those good days in a software engineering project. So let me say a little bit about what this thing is used for. And this is a body of work that I particularly like. It's focusing on an energy problem. So this is a map of the southern half of the UK. And this big estuary that we see over here is what's shown in enlarged form here. And it's been proposed that we should build a dam across this estuary. Now, as you might imagine, there's a huge tidal flow back and forth with every tide here. And there's enormous energy capture potential. But there are big, hard questions around the environmental impact of this intervention. So in this paper, and also illustrated on the Thetis website, the Thetis is this coastal ocean modeling tool that builds on Firedrake. We have actually modeling the way the way the tide flows into the estuary and flows out, and we can start to estimate the energy that is potentially captured here. We can also model, for example, the way wetlands are the way water flows over wetlands and so on. I'm not the applied scientist. This is fun to talk about at parties, but it's not my work. So where I'm going with this is a big claim. Claim that we are building power tools for performance programming that actually do productivity, performance, and performance portability. I mean that from a single Python script, like the one I showed you, we can generate code that is pretty fast, that is fully portable. There's nothing in that code that says what kinds of backends it's running on. And meanwhile, we're supporting a level of abstraction that enables our users to focus on their domain of expertise. This is probably the single most important thing of all this. I once had a chat with a computational scientist, and I was talking about iterative compilation, where the compiler iteratively searches for the best combination of loop tiling, for example, that kind of thing. And this guy said, this is complete rubbish. You're completely misdirected. Not because it doesn't work, but because all the big opportunities actually above that level of abstraction. All the big opportunities are to do with solving the right equation with the right numerical method on the right kind of mesh, this kind of thing. And my objective is to build tools that enable other people to do just that, to be able to change the way they're modeling a glacier flow and press a button and have it working right there and then with no, let's spend some weeks implementing this new model. That's the plan. Right. So is it just Firedrake that pulls this off? We have another project that I wanted to talk about called DeVito. And DeVito is a kind of child of Firedrake. My colleague, Jared Gorman here, got interested in full waveform inversion for seismic imaging and thought that he could do it in Firedrake. And for reasons I don't completely understand, it turns out that everybody does this with finite difference, not finite element, for some good reason. And so he said, well, in that case, what we need is a Firedrake for finite difference, which he calls DeVito. Fabio is one of my PhD graduates whose thesis is on lots of things in Firedrake. And between them and now a team, and indeed a small startup, they have a fully open source implementation for essentially the same idea. By which I mean that you type in the partial differential equation, you specify the discretization, and we generate the code. So it's largely driven by seismic inversion applications. One of my favorite applications I'll show you in a second is ultrasound imaging of the brain, which is actually the same numerical methods being applied. Yeah, so here we go. This is the ultrasound imaging. So we have a patient, we have a hat with lots of ultrasound sensors and a transducer that generates an ultrasound signal. We can use DeVito to model the way the sound wave moves through an estimated or guessed brain structure. The full waveform inversion algorithm is the mathematics that enables this to work, even though there might be like a skull in the way. What we actually do, of course, is when solving an inverse problem. So we use access to the adjoint, to the automatic, or to the derivative of this solver, to apply essentially a backpropagation algorithm to iteratively solve for the internal structure of your skull. So this is not stuff that we did. Friends and colleagues picked it up. Luis Garash is the lead on this project. And for me, this is another story where we're trying to enable those people to live in their domain of expertise. So we perhaps needn't go into So this is another fully, in some sense, complete Python script. We're setting up the mesh, the problem. We're defining, so this is the PDE. Here's the maths for the PDE. Here's the transcription. We automate generation of finite difference stencil by automating the textbook mathematics. A key thing in these acoustic problems is that we need to inject a sound signal and to model what a receiver does. So it interpolates the signal from various neighboring mesh elements or grid points in order to estimate what a microphone would receive. We put all that together and we can time step this thing. Having written the script, you might ask, well, I can run this on my laptop. Actually, I can take the same script and run it fast in MPI on your cluster, your laptop, your supercomputer. And if you want it to go on your GPU, on your laptop, or your supercomputer, then you just add more environment variables. This stuff, at this level of abstraction, is being used by DeVito customers day in, day out. And without very much low-level hacking, I would love to claim zero. It's mostly zero. So I show you a little bit of the optimizations that happen in DeVito. And this is analogous to that lifting loop invariant expressions out. In finite difference stencils, we have recurring terms that are common from point to point. Neighboring points have common terms. And optimizing that is particularly valuable and important. So in this example, this slide only shows the low space order 4, so the stencils are quite small. And without optimization, the solver takes 287 seconds for this example problem. With aggressive optimization, we dramatically reduce the operational intensity. We make this problem harder in the sense that it's more memory bound, but it runs faster. If we increase the spatial order, so here we have spatial order 8, let's go straight to the match, right? Spatial order 16. We now see a factor 3 performance improvement thanks to this optimization. And we transform something which is extremely arithmetically intense into something which is memory bound. And this motivates us to study things like space tiling and time and that kind of thing. And here's tiling and time. So here we have tiling and time is where we grab a patch of the mesh and we advance multiple time steps whilst keeping all that data in the cache. And then we move on to the next patch, the patch that fits into cache, and we do the same thing. At low space order, this gives this kind of performance improvement from roughly something in the region of 40 or 50% performance improvement. At very high order, it actually gives almost no performance advantage. And for many of our seismic inversion problems, actually we're living in a fairly high order regime. For things like fluid dynamics, this is potentially actually quite a big deal. So I actually managed to not have a clock, so let me know if I'm running over time. So I thought I'd wrap up by talking a little bit about compiler architecture and how to implement it, by talking about this paper. And for more details on what I'm showing you, you might refer there, and also to this XDSL project that I linked to here. So what the diagram shows is, on the top, we have 3 different DSLs, and they're all basically finite difference stencil DSLs. So this is DeVito that I've talked to you about. This is a project from Zurich, the Open Earth compiler. It's a climate code. And it has its own stencil intermediate representation, its own compiler backends, and it generates code for GPUs and so on. Cyclone is a DSL being developed by the UK Met Office, again, for somewhat different problems from the ones I mentioned earlier. And again, it has a finite difference stencil intermediate representation. What is frustrating about this is I showed you a slide earlier on that said DSLs tick performance, portability, productivity. Each DSL seems to involve a complete vertical stack of specialized code for a particular DSL. And we kind of found ourselves reflecting and writing a grant proposal around the question of, if you want to run with this, we need to make it scale. And to make it scale, we have to get people to share common compiler infrastructure and use it to economize on the effort involved. We also want to start building bridges between DSLs for different numerical methods. An obvious one might be finite element and particles, for example. And finally, a third thing is, if you've got some fantastic idea for how to do stencils better, then historically what people have done is they've implemented it in their own silo and compared it with somebody else's silo, and that's great. In a better world, we would implement it in a common compiler framework where we can see the impact of what you've added in addition to all the other tricks that we know how to do for all the applications that are supported by the different DSLs that target that toolchain. That's the ambition here. So in this paper, we take these 3 and we re-architect the compilers of all 3 of them to share a common intermediate representation. And I'll show you performance numbers in a moment. Get nearly the performance that each of these separately gets. Or sometimes better, sometimes worse is probably the better way to look at it. But the point here is that hopefully we can benefit from a long-term software engineering advantage of this unification. I'm telling you about this, hoping that you will do the same sorts of things in your world. So this stencil intermediate representation is defined, and if you know anything about this, you've already thought this is an MLIR talk. And it kind of is, except that all the tools that I've mentioned so far are 100% Python projects. And this is a very good reason. We started out in C++, and we had a revolution amongst our developers, and they promised they could throw away all their C++ code and re-implement in Python and get back to where we were within a month or two, and they did. So the performance advantage here, the productivity advantage, we built a Python rendering of the MLIR abstraction with an automated two-way street to the C++ MLIR. You can build an MLIR in MLIR, export it into XDSL, do stuff here, re-import it back into MLIR, and you can do the same thing in reverse. XDSL is sitting there waiting for you to give it a try. There are tutorials, there's a user community that I'd encourage you to join or play with some of their tutorials and see how it goes. In Imperial architecture, the starting point is the stencil DSL, so somewhere in the middle, there's some code that actually does the arithmetic of your stencil, and in real examples, this will be more complicated. The important thing is this access descriptor here that describes how the data is fed to this kernel from the grid, from the mesh. And this is what encodes the stencilness of a stencil. So what we then have are two further MLIR XDSL dialects. One is distributed memory parallelism, where we derive the bulk communications that need to take place. We derive that from the dependence that we know the stencil has. And then we have a dialect for MPI, where we lower that fundamental communication requirement of the problem into a elaborated implementation. So on the left, we have the stencil DSL. Here's the distributed memory parallel version of that same thing. And then here it is lowered to actual MPI calls that you might recognize. For your problem, you might well need MPI, but you may well find that our distributed memory parallelism model is a little restrictive for your problem. You may well find that the stencil is not what you need, and you will need to define your own MLIR XDSL dialects for these. And this is where the design or the compiler architecture, the artful design of representations that actually make this work, comes in. So here's DeVito mapping into the stencil dialect, and from there we can get code for GPUs and perhaps even FPGAs. We're actually working on backend for the Cerebrus machine as well. For the Cyclone DSL, the Met Office one, this is a DSL embedded in Fortran, so there's lots of complicated, horrible parsing, which you don't have to do if you start from Python. And from there we get two parts. We get the Fortran intermediate representation that they're using in their Cyclone DSL that generates essentially the sequential wrapper for your code, and then the stencil dialect is extracted from that. And we could spend ages unpicking the performance results from this. The point is that it's kind of competitive, and with more work, it could certainly be as good as anything we've done before. Occasionally, it's actually better, as we see in this column. Let's not get dragged into that. So I should take a breath and wrap up. This is my final slide. What I've tried to do is to give you a kind of tour of some of the things we've been doing. And what I intend to do is not just to tell you that you should be users of our tools, but instead to communicate some of the things we've learned in building them. So the first one is, if you want this magical combination of productivity, performance, and portability, I mean, you can hear people talk about this in high-performance computing environments all the time. And this is the motivation for many, many, many high-level parallel programming models. Many, 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 because it's actually a hard problem if you think of it as a general problem. If you are prepared to start from a domain-specific context, then you can have this today. You can have it really today by downloading the tools I've mentioned and running them on your laptop this afternoon. You can have it today for your problem if you're prepared to commit to building code generation tools for your specific class of problems. And in doing this, I think one of the big lessons from me, and the heart of it actually is that example I mentioned to you earlier on, of taking all that code that was working on the loop trees to do clever domain-specific optimizations, and realizing that we could lift that into the tensor contraction representation and just do it by a factorization. And then the rest of the toolchain is simple. That kind of thing is, for me, the definition of winner. It's when the right representation makes this messy problem into an easy one. And in my mind, our compiler architecture has really two big ideas: the tensor contraction, also the access-execute model, that idea that we have kernels and we have a declarative description of how to feed the kernel. And that, for me, is another important part of what we've been doing. You might wonder, do we just build different ones for different problems and sit back and enjoy? For me, the grand problem, the grand ambition here is to generalize this, right? Generalize it in the sense that we can pick off different application segments. So I mentioned earlier on, we tried to do this in density functional theory. It turned out to be really hard. Quite in different application areas, ideally using common compiler infrastructure, and perhaps even thanks to using common compiler infrastructure, actually getting some kind of composability of these DSLs. Or if not composability, at least I can say, well, I can solve my problem with this numerical method and therefore this pathway, or I can take the same abstract specification of the problem and choose a different code synthesis pathway via a different numerical method. This kind of thing. And then suppose I want to solve this fluid problem, but I want to transport particles in the fluid. We should be able to just glue these things together. Where else do we get the abstract for this? Talked a little bit about pointer aliasing, and I mentioned earlier on that this is a kind of fundamental barrier to what compilers can do with general purpose code. Another way to look at it is to say, well, one of the key things your DSL does is it knows about your data. Actually, our DSLs also know about the computation, but just knowing about the data is a very big part of this. Okay, that's enough from me, and I invite your questions. Thank you very much indeed.
Okay, thanks a lot, Paul. This inspiring talk. All right, so are there any questions? Please raise your hand, unmute yourself, put it in the chat, whatever. The discussion is open. I have a list of questions, so I can just start. So first, a very high-level question by me. So you aim at reducing the compiler Turing tax, but looking at the amount of software you built and the diversity of all that software, I guess that by reducing the compiler Turing tax, you're sort of increasing the software diversity Turing tax, because you have this explosion, this Cambrian explosion of software and variety. And you said yourself that building all this for density functional theory proved to be harder than anticipated, and it may be even harder for other fields of science. So is it worth it?
That's a good question, but it's kind of the fundamental question. For me, if you were doing all this code generation for just one problem, like if you're motivated by solving one specific complex flow dynamics problem or something like this, then you might think, well, we could just like code this up, perhaps using powerful libraries like June or something. Why would we need a program generator? And why would we need that program generator to be generalized in the sense that it handles a whole domain-specific language of problem instances? Well, sometimes it's actually easier to write high-performance code by writing a generator that generates high-performance code. But that is a hard one. That's a hard one to win, so maybe I shouldn't pretend to win that one. Is to build tools that generalize, build tools that handle a whole problem space. So, I mean, the simplest thing that I showed you in that vectorization performance graph was you can just crank up the polynomial order, and it's just a number in that Python script. It changes the computational structure in quite complicated ways. It might even change the optimum vectorization strategy, that kind of thing. Toolchain just looks after all of that. And so it's not always a winning strategy, but when you can make that generalization pay off, it is. So that goes some way towards answering your question.
Yeah. We could talk about that over a couple of beers, maybe.
Sounds like a good idea.
Jan raised his hand. Go ahead, Jan.
Yeah, another concern I would have as a programmer is that I depend on a lot of external software. And so in an ideal world, of course, everything just works. But as we know, software is never ideal. And there are always bugs. And it's not only bugs, also maybe the requirement changes, maybe the interfaces don't match as well as anticipated. And then it might be very hard for me to fix things, because it might be buried in this stack of software complexity. And I just cannot fix things. I rely then on external software. I don't have direct control over it, and I depend on it,
Kind of jump in and say, well, what I think your question is about is a very anticipatable question, which is that there are barriers to uptake for domain-specific code generation tools like the ones I've presented. And they're very rational barriers to uptake, like, we've already got a code base that does all this. Why would we refactor it to use your tool? If I'm considering adopting your tool, do I have faith that your tool will handle the unanticipated extensions of my project that might go beyond the scope of what the tool does? If there are bugs, how do I debug it? How do I do performance analysis on generated code?
Yeah.
I want to build tools that have access to the mesh, but the mesh is a private data structure inside your DSL. Is this the kind of thing you're concerned about?
Yeah, the transparency and also how to fix errors. Yeah. So, but now let me, you can follow up, but now I remember what I wanted to say.
Yeah.
The second aspect is that the broader community loses the ability to apply those kind of things. They loses the knowledge, like even to program an MPI. Similar to AI, people always tell you, it's great, you don't have to bother anymore. Yeah, but most people will lose the knowledge and the abilities to do things. It's like my car manufacturer, so my car repair garage, they can't repair anything anymore because they never do it. They just exchange parts because it's too expensive to repair stuff. And so they didn't learn it anymore. They can't do it anymore. And so I think it's similar then. If you never do this stuff, a lot of people will lose the ability, and also the newer generations will lose the ability to do this. And the knowledge about this will then be concentrated to a very small circle. And I think that's a big problem.
May I respond? You and I share a pride in doing engineering right. And part of that pride, in my mind, is to enable other people to have faith that we will take it from here, right? You present your code to our tools in a suitable way, and we will look after the stuff that is our domain of expertise. And our service as professional engineers is actually to support our users in being able to do that. Our users are fantastically expert people. It actually troubles me when these fantastically expert fluid dynamicists find themselves also very expert CUDA programmers. I want those people to be living and navigating their domain of expertise, using the tools that we give them that enable them to do so efficiently. That came over as a speech.
Actually, the car analogy is not bad in this context. I consider myself to be a decent driver, but I have no idea how to adjust the ignition timing on my engine. I leave that to other people who know how to do that. And I can still be a good driver even without knowing that. Yeah. So there's always a question, where do you draw the line? Or where is my abstraction, my personal abstraction boundary, where I say, okay, I leave that to the experts.
I agree. I mean, I'm not a domain scientist, yeah, so I'm sure domain scientists have a different view on that and maybe agree with your offering, yeah, that they don't have to bother with this kind of stuff because it's not directly related to what they are interested in.
I could continue responding to this, but it might be interesting to hear other people's view on this question.
There's nothing in the immediate context, but there's a question in the chat. What are some pressing matters in DeVito and Firedrake or DSLs for simulation in general that are interesting to you other than generalization?
That's a good question. Yeah, I mean, there are many, many directions open up here. That ultrasound imaging of the brain project, those people came to us with a Fortran code running on a cluster, and it was taking them a couple of days per image. They bravely recoded in DeVito and got it running on a cluster of GPUs in an hour or so. The clinical value of ultrasound imaging of the brain, and there's some, even if you have to wait for a day in the cloud, there's some, if there's more, if it's an hour. There's a lot more if it's 10 minutes while the patient is still in the ambulance. And beyond that, and we had meetings within that project with neurosurgeons, they want this computation to be happening while they're holding the knife, right? Sub-second. There's an escalator of potential performance there. And the question for me is, how could we possibly get those multiple orders of magnitude of performance? Some of them come from numerical methods. Some of them come from using yet more exotic architectures. For me, this is one of the reasons we've been looking at the Cerebrus machine, for example. That's one kind of challenge. I found myself very interested in exploiting the properties of meshes, not just somebody gives you an unstructured mesh and you then try and derive structure from it, partition it and color it and so on, but also looking at how meshes come to you. The meshes come by composition, for example. Meshes, for example, in fluid structure interaction problems. We should be able to use the provenance of a mesh, or the way it was composed, to optimize the code that solves the right equations on it. What else? Yeah, I mean, we're doing more of the usual stuff, building better GPU backends, thinking about exotic alternatives to GPUs. It's not my work, but there are Firedrake people working on things like plasma simulations that require fully integrated particle and continuum models. That I think is potentially very exciting, but it's not something I've been involved in. But it's technologically quite messy because, of course, you think about how you should partition and load balance and so on for locality and efficiency. I'm sure there's more. What do you think we should do?
While Peter's thinking about that, I'm taking a little bit here of asking the last question. At one point in the discussion of the inverse problems with DeVito, you said something like there was mostly zero low-level hacking. And what bugs me in this is mostly zero and low-level hacking. So what was the low-level hacking and where was it applied?
So DeVito is primarily an open source project, but there is a very small startup that handles relationships with paying customers. And there are performance features that are in that code base that are not in the open source code, particularly to do with some of the GPU optimizations. So what I would like to say, and I think this is true, is that the low-level performance hacking was done by the DeVito team, not by the customers.
So it was adjustments that were necessary to address a particular backend in an optimal way.
Exactly. And I believe that it's done so in a way which is in the generator. It's benefiting multiple example input problems.